The broadcast is now starting. All attendees are in listen-only mode.
Well, hello and welcome, everybody, and thanks for tuning in today. This is the kickoff of our 2013 Copy with Caleffi series, and we've got a good lineup of the first 6 ones already listed online, and I think it's going to be another interesting lineup for us. Today I've got a presentation that Jeff is going to help us with. I've known Jeff for years. He's a longtime member of the RPA. We've been a friend, and he's a friend of the industry. He writes for different magazines. He's got a new book out that we'll show you at the end where you can go to buy that. This, I think, is probably one of the biggest and most overlooked issues in our industry is fluid quality. I mean, I don't think a lot of people know what they should be doing or how they should correct problems with systems. So Jeff has tons of experience in this. He's been doing this for years, not only in hydronics, but in geo systems and probably some solar systems. So it's more of a stealth type of issue. It's not something like a relay with a wire off that you can find and diagnose and fix easily. It's something that, you know, sometimes takes years to present itself. But there's a few little things that you can do on the front end with the systems when you start them up that can avoid a lot of problems, and that's what Jeff is going to he's going to tell us about today. So, Jeff, tell us a little bit about your background and what you do and what you like to do, and away we go.
Well, certainly, Bob. I want to thank you and the folks at Caleffi for helping to put this webinar together. From my standpoint, I got into the industry as a groundwater geologist, and my focus was towards the geothermal side of the industry because this takes us back into the mid-1970s. And we were all looking for ways to avoid the increased cost of foreign oil, et cetera, and be more energy independent. So early on, I worked through graduate school with water chemistry and geology, was an associate with the National Groundwater Association, working on various studies with them and working on publications that involved geothermal heat pumps. That involved into manufacturing, and then finally into operating my own business and assisting other contractors with geothermal projects. So I'm pulling together perhaps over 35 years of experience, and I like to present that experience through good stories in hopes that those who follow us will be able to avoid some of the problems we've encountered and improve their profits along the way. So that's it in a nutshell for right now. But shall I move on and try our first slide?
Yeah, and your experience, I mean, you do big systems too. You work on like universities. It's not just little residential, but I mean, I think you told me once you've looked at thousands of systems over your career, from, you know, little residential all the way up to some of the biggest universities and stuff around. So
yes, residential systems up to several thousand tons.
Right. Well, yeah, I'm excited. I know we did a presentation last year that I sat in on, and that's what triggered this whole thing. And take it away.
Okay. Well, we want to start out talking about dirt and air. They really do matter. Neither one of them are friends in a closed piping system. It doesn't matter if it's a boiler, cooling tower, or a geothermal system. Those are all closed piping systems. And the chemistry of the fluid that circulates in those systems will determine the longevity and the service and maintenance that those systems require for their lifetime. Unfortunately, not everyone has a good background in water chemistry, and a lot of specifications are written that they be filled with potable water. And from my own experience, there's a wide variety of chemistry that might be considered as potable, but that doesn't mean they're acceptable for use as a boiler fill or as a geothermal system fill. So the best way to maintain happy customers and prevent corrosion in new installations is to use inhibited antifreeze products, and also use distilled or deionized water as a system flush and fill solution. All too often, like I said, specifications may state the fill solution be potable. The minerals in potable water, it can be hard, it can be soft, it can be a low pH or high pH and still be considered potable. But all of these things have a dramatic effect on the tendency to promote scale or corrosion within a hydronic system. Probably First of all, in this corrosion issue would be an item we talk about called the galvanic chart or galvanic scale. We have noble metals, which are very resistant to corrosion. They're at the top of the scale, and those would be items such as graphite, gold, silver, titanium, stainless, things that we think as being immune to relative corrosion. And then we have minerals that are, or metals that are very easily corroded. At the lower end of the scale, zinc being one of the most easily corroded, followed by aluminum, tin, lead, steel, iron, copper, etc., as you head towards the middle. And when you have two dissimilar metals mixed in a solution, you can always set up a galvanic or a battery cell. So in this slide, we have a penny tied to a digital ohm meter or voltmeter and a galvanized nail, and they're both sitting in city water. And we have a voltage circuit there that's 8.75 volts, wherein the electrodes are transferred from the zinc coating on the nail over to the copper penny. And we see the same type of battery cell exists inside our hydronics. So there's your galvanized nail, and the electrons move from the nail to the copper penny. When we started with one of my class programs at Hocking College, one of the questions was, well, what happens with these solutions? I said, well, let's set up a lab experiment. And we did 40 different sample containers. We experimented with distilled water, deionized water, well water, city water. We used inhibited propylene glycol as an antifreeze. We used methanol, which is a very common antifreeze used in some geothermal systems, not that it's necessarily potable, but it's often used. And we wanted to see what reactions we'd have with different types of water. So here's an example of an inhibited propylene glycol mixed 20% with deionized water. The sample remains clear after 6 months of shelf time. The steel wool in the sample shows no sign of rust or deterioration. Here's a similar sample of propylene glycol. Again, this is 20% mixed with well water. And what you're going to notice in this well water solution is a heavy layer of sediment at the bottom of the container. And you can see some white sediment on the steel wool sample also. And the steel wool is starting to show some signs of rust and corrosion inside that sample. So what's happened here is that the mineral content in the well water has complexed itself with inhibitors in the antifreeze, causing those inhibitors to precipitate from solution and rendering that propylene glycol as a corrosive solution. Now it's no longer protecting the metals in the system from corrosion. And here we find a sample that is 20% methanol, that's racing alcohol, in deionized water. And you can see the amount of corrosion in there on the steel wool sample, the accumulation of some sediment in the bottom of the jar, and some staining on the sidewall of the container. Whoops, back up here, sorry. And then here is a sample of methanol, 20% in well water. And it could just as easily be city water, which has more minerals in it. Similar to the well water in many instances. But this sample shows significant signs of rust and deterioration after only 6 months shelf time. There's sediment in the bottom. The wall of the sample jar is so obscured it's hard to see what's inside it anymore. And it's unfortunate, but for the vast majority of installations that we may encounter, we find that the antifreeze is mixed with city water or well water from the site that the installation was made at. And these are the conditions that are existing inside the systems. They're the systems or the mechanisms that are leading to corrosion of ferrous body circulating pumps and other ferrous metals inside those systems.
Hey, Jeff, can I interrupt and ask a question now on the
Yeah.
methanol? Is that because there's no inhibitors in the methanol compared to the propylene glycol? It seems the glycol ones lasted better, but they don't put a lot of inhibitors or chemicals in the methanol that's typically used in a geosystem, or is that just off-the-shelf stored methanol?
That is correct. The vast majority of the methanol-filled systems, let's simply say that the methanol is racing alcohol added to water on site. There's no corrosion inhibitor in there. You've got the hardness minerals that exist in the original water fill. If I tell a story, this will take us back into the 1960s and 1970s. There's before BP was Sohio, and they had a gasoline mix called Sohio with Ice Guard, and the Ice Guard was actually methanol added to the gasoline because the methanol would easily mix with water in the gas tank and prevent fuel line freeze-ups. Unfortunately, during that same period of time that people were religiously using Sohio with Ice Guard, they were experiencing leaks in fuel lines, leaks in gas tanks, fuel pump failures, and carburetor problems. And it all related to a very corrosive issue between the methanol and the ferrous metals used in construction. So carburetors have evolved. We're using ethanol in our gasolines, but their metals and their gaskets and seals and so forth are made to help withstand those corrosive actions these days. But it was a good lesson from way back when, and methanol still is quite corrosive when mixed with tap waters and used as an antifreeze solution.
Right.
I hope I answered that.
Yeah, no, that's what I wanted to hear. I mean, even if the methanol was mixed with a good quality water, like a deionized or demineralized water, it still doesn't have the inhibitors. And one of the inhibitors, from what I understand, that they put in propylene glycols is to lock up that hardness and to lock up some of those bad things that in the water that you blend it with. It's not to protect the glycol, it's to protect the water that they're blending in at the job site. So unless you're buying pre-mixed where they've mixed it at the factory with a deionized water, the water that you're putting in, the chemicals and the glycol are in there to lock up some of those problems, and you don't see that in the methanols. Even the fluids you buy specifically for geo systems don't have, which is why probably they're less expensive and people use them, because they don't have to put all those ingredients in there that drive the cost of the glycol solutions up.
That's exactly right, because you can buy uninhibited food-grade propylene glycol at a substantially lower price than you can purchase the inhibited propylene glycol. And there are some sources out there now that have I want to say it's an FDA-rated inhibited propylene glycol, and they work quite nicely. But again, those are products that are either mixed at the factory with deionized water and shipped to the site as a premix, or must be mixed at the site with deionized water. They're not intended to be mixed with tap water from the site. No. This is an example. This happens to be sort of a sideways view of an atmospheric type geothermal flow center, showing two pump bodies with let's say the initial stages of advanced corrosion from a chemical cocktail made up of methanol and calcium chloride. It's an unfortunate circumstance, but a second subcontractor in the process of replacing equipment opened the loop and decided he'd prefer to work with an open flow center. Did not realize that there was calcium chloride in the original system. It was just a clear fluid, and topped it off with methanol to increase the antifreeze strength of the system. So now he had calcium chloride, which is corrosive by its own nature and becomes extremely aggressive when it has oxygen contact, in an atmospheric flow center and mixed with methanol at the same time. And this particular flow center chewed up, I believe it was 6 circulating pumps in about a 2-year period of time, just from corrosion and failure, and the corrosion products would get in around the wet rotors and lock the pumps up solid. So it was quite the problem until it got corrected. And correcting the problem meant flushing the loop with DI water several times over to get it cleaned out, and then replacing that fluid with an inhibited propylene glycol solution to take care of the problems. It's very expensive. It's not something you want to have to go through. Oh, and this is a great example. There may be some people listening in on the conference who have incredibly soft water. This is water that still stays slippery after your shower. So I can't get the soap off. It's so soft. This happens to be a bronze body circulating pump from a system with very soft water. It was on a hot water recirculation circuit, and the home had a stainless hot water tank and a stainless preheat tank because they knew they had some corrosive issues with the water in the area, and they thought that by using the stainless they could avoid problems with replacing repeat water heaters. Well, the next, shall we say, least noble material in the system to those stainless water tanks was the bronze pump and the copper piping in the home. And the customer was complaining about green stains in their sinks and tubs and so forth. I really didn't take too much stock in it until I got a call that said, we've got water on the basement floor and it's coming out of this geothermal machine, and we found this circulating pump essentially totally eaten up on the inside of the pump body. Solution for this problem was to install polysulfone, high-temperature plastic container in the recirculating line for their hot water system and put some magnesium rod sacrificial anodes into it. And so here you see a couple depleted sacrificial anode rods with their center cores on the left side, and some other rods in the process of being depleted that were taken out of that canister. Once those sacrificial anodes were installed in the system, the green stains in the sink stopped, and we've not been back to replace any pumps, and thank goodness there haven't been any perforations in the copper lines in that pump. But it was a matter of having an aggressive water supply, a very soft, hot water, shall we say, can dissolve a metal. Let's see, the solution rate doubles for every 10-degree increase in temperature. So if you start out with 50-degree water and you increase it to 120 degrees, you've increased the solubility of metals in that system many, many times over by the time you get it to 120 degrees. And if you've got a little pump there that's running 24/7, that just accelerates the problem. So in those situations where someone might be circulating water for a hot water return circuit, I might suggest make certain you've got good sacrificial anodes in your system, and also perhaps, if possible, put those pumps on a timer so that they're not running 24/7. I've read where casinos in Las Vegas sometimes have to change their plumbing and fixtures perhaps every 5 years simply because of corrosion in the systems, and that a lot of the piping out there has had to go to CPVC to try and avoid problems because of their soft water situation.
Jeff, you mentioned the situation was with aggressively soft water. What would you consider to be defining soft water? Is it in grains of hardness? Is there a measurement there that you would say would be too soft?
That's a loaded question. There's a very complex formula. It's called a Langmuir index, and at this time that's something you'd have to look up online, look up Langmuir index, because you're looking at pH, you're looking at the minerals in the water, you're looking at chlorides in the water, sulfates. There's many different factors in there that are going to say whether the water is going to be aggressively corrosive or a scale former or neutral based on the temperature that you're working with. And So I could say, yes, low grains of hardness means that it's a soft water and it could be problems, but not necessarily. There's other factors involved also.
I remember too, Jeff, is when indirects became popular in the market, and people said, well, yeah, you can put a much smaller indirect than you would have with a gas-fired water heater because you've got the horsepower of your boiler and they recover quick, and you're going to have all this hot water and never run out. Well, that wasn't necessarily the case with homes with big dump loads and stuff. So what did they start doing? They started cranking them up, and so they'd crank those indirect water heaters up to 140, maybe 160 degrees or even hotter, and put a thermostatic mixing valve on them. Well, now that multiplier that you talked about a second ago really dries up when you start taking your tanks up to 140, 160, and you've got really aggressive water now. So, we saw failures in the stainless steel tanks. We blamed it on the welding. We blamed it on the grade of stainless, and it in fact was those elevated temperatures were just really making that water that much more aggressive to the tank.
That's true, and there could be an instance here where chlorides, if there's some salt to that water, and you know that when you soften water, you're adding chlorides to the water as a means of removing the minerals. Those folks who are doing saltwater swimming pools, we have to be cautious as to what type of heat exchanger you may interface with the saltwater pool. If you're heating that from solar or geothermal or with a boiler or such, the chlorides in the saltwater pools will cause stress crack corrosion on stainless. And we have to be careful about what's used, what grade of stainless, or if we go to a marine-type brass, copper nickel, or such heat exchanger to handle those situations. So, like I say, it's a complex problem and a complex answer sometimes. I wish it was as easy as saying yes or no, but there's no straight yes or no to it.
So at some point, bring in a water expert if you have ongoing problems that you can't seem to get a handle on with pinholes in copper or bronze pumps starting to leak and stuff like that. I mean, you really need to get somebody that knows how to analyze all those different things, and it's not just going to be a little, like I have in my truck, a softness test kit where you can just drops and count how many grains. Like I say, you got to know the pH, the TDS. It's not something that the average plumber is going to probably have the ability to test that on the job site, or even the knowledge to know what needs to be adjusted or changed to make it a viable fluid for the system.
That's very true. And for those out there with some well water situations, most well water is going to have dissolved carbon dioxide in it. We don't think of our well waters as being, say, effervescent or carbonated, but there is natural carbonation in those well waters. And as you heat them, you drive out the carbon dioxide. And that upsets the chemical balance, and then things become scale forming. But carbon dioxide by itself is carbonic acid. So you can have a cold water supply with lots of carbon dioxide in it, and it's very aggressive.
Jeez, yeah.
So that's where the groundwater side comes into things. Well, let's move on here. Here's a commercial geothermal, which runs at, say, temperatures between 40 degrees Fahrenheit and 70 degrees Fahrenheit. This building was piped all in black iron pipe. It circulates around to 22 horizontal geothermal machines above the ceiling. And within about 5 years of its construction, it began to experience leaks at brass to threaded black iron connections. And it was all attributed to a combination of galvanic corrosion and methanol in the system. And we abated that using the sacrificial anode rods in a canister and a simple bypass here at one of two primary pumps for the system. It worked quite nicely. Here's an issue that you'll find that occurs frequently with soft water, and it's dezincification. You might remember from the Galvanic series that zinc is very low on the Galvanic series, and our brass contains copper and zinc. the water can aggressively go after that zinc, dissolve it from the brass, making the brass porous, and you start to find this white crust from the minerals in the softened water coming out through the brass valve. Now, sorry, background noise will quiet itself down in a moment. We have situations where a lot of our brass valves and materials are now coming from overseas sources, and I might say perhaps they're recycled and they may have a higher zinc content than what pure copper may have had from years ago. And it's something we want to watch out for. I watch refrigerant coils and I question why we see so many leaks in refrigerant coils of recent, and I have to question if it might be within the chemical makeup of that copper, if there might be some residual zinc there. Those are yet to be answered, we'll put it that way. But this is what happens in a water system, and if you notice a structure where you see the white crust building up around brass valves, you know that it's become porous, you know that it's become weak, and if I ever find a gate valve that shows evidence of this on it, I'm very cautious about how much tension or pressure you put on those gate valves, because the threaded mechanism that raises and lowers the gate may just give away if you're trying to tighten the valve closed or trying to open it from a closed position. I've had to replace many with ball valves because the gates remain stuck in position, and it's because of this dezincification type reaction that occurs in raw water supplies.
Well, that's a good tip. I've seen that on valves, and you're right. You grab a handful of that knob and you turn it, and you might just have it come off in your hand and have a substantial leak in your hand.
Or suddenly it spins and you can't figure out why. There's no circulation in the circuit.
Yeah.
Oh no, that valve is 50 years old. Now what am I going to do?
Yeah.
This is a great slide. It came to me through one of our commercial suppliers, and I was just totally knocked off my feet when I saw it. This bronze or brass pump impeller is 1 year old, and it was on a variable frequency drive motor that had experienced a high voltage surge. They ended up replacing the drive unit on the motor, but did not replace the motor. And my suspicion is that there's been some winding damage in that motor that's causing stray currents to pass through the shaft and dissipate into the fluid that they circulate, because the plumbing system is copper that it's connected to. And it shows almost complete I want to say electrolysis depletion on the impeller of this pump. It would be something to watch out for and make certain that there's good grounding for things. And if you do experience problems with motors and drives, that you're watching for stray electrical currents. And when we talk about open systems that are working with well water, this is a simple galvanized T with a brass nipple inserted to it, so you've got a combination of galvanic corrosion going on there, and you've got the action of a raw well water, which literally chewed a hole through it and create quite a bit of water damage in the area where this was located. So you never want to use ferrous metals with raw water supplies. You always want to work with brass, stainless, PVC, CPVC, essentially non-corrosive metals when you're working with raw water.
So the galvanized went to the brass or vice versa, and that caused it to be then just a black steel fitting inside once the galvanized coating went away?
That's right. It was just turned to black steel. The battery cell was there between the black steel and the brass, and it goes right through. It's a little bit a little wry humor here for the plumber in all of this. The dielectric unions that are used at the top of hot water tanks are primarily steel, connected to copper piping, and they become a bit of the sacrificial anode in the system once the anode rod in the tank disappears. Usually those galvanic or those dielectric couplings become pretty well plugged up from corrosion or eventually perforate.
Well, and the same thing there, I would say, Jeff, is, depending on where they were manufactured, the quality of the zinc coating that's put on there, once that goes away, I mean, if they're not plated well, or if they're not plated with a good quality, then you're right, you just have a steel fitting on there.
Yeah, once it goes, it's gone. You're right. And it's a rapid process. It doesn't take too long. I'd say within about 18 months of the depletion of an anode rod in a hot water tank, if you have an aggressive soft water, is about the time you see that tank perforated someplace where the water can get through to a raw steel area where a threaded coupling comes into the tank, or where there might be an imperfection in the glass lining on the tank.
Well, now on this one here, the water too had something to do with it, because that's the electrolyte, I guess, in it. So depending on what the quality, the condition of the water can make that speed up or slow down. Like I said, the water and the hot water too would make that happen quicker.
Yes, that was the water, because it's raw water, it's well water, it's mineralized water, and mineralized water carries an electric current. Deionized water has no minerals to it, same with distilled water, and will not carry an electric current. So I could essentially stand in a bucket of deionized water and touch a live electric line and not electrocute myself, because the water does not conduct the electricity.
But don't try this at home.
Don't try it at home, but if you're out in the desert Southwest, insulators on high tension lines accumulate dust. And if there would ever be a sea fog situation come in off the coast or some moisture, that dust becomes electrically conductive, and those high tension lines can short the ground. So utility companies will come around with a water cannon truck and deionized water and spray off the insulators. And it's safe to do that from the ground, because the deionized water will not carry that, say, 14,000 to 48,000 volt charge from those high tension lines to the ground. It will not conduct the electricity, so it's safe to clean them off. This slide that's up right now shows a pile of brown debris, and this is actually redeposited ferrous material from a ferrous piping system, from a black iron piping system. This was redeposited inside the rubber flexible hoses that are used to connect between the geothermal machines and the piping in the building. And at the time I was replacing the machine, I thought that these hoses were fatigued with age. And I said, we're going to cut these hoses out and replace them because they feel hard and crunchy. Lo and behold, the hard and crunchy inside the hose was redeposited ferrous metals from in the system, and not the fatigue in the hose itself. The hose was perfect after it was cleaned out, but just squeezing or flexing the hose gave you this crunchy feeling. And this is the material that was coming out of the hose. The grid behind this is a 1/4-inch scale grid. And so some of these flakes are well over a 1/2 inch across. The system this came out of, I had a 30-gallon trash can. Pump strainers kept plugging up, and we ended up taking them apart and flushing from the system there, using hammer drills on the sides of lines, low places in the lines, to try and agitate stuff like this to get it to liquefy and flow along with the system to get it cleaned out. And we eventually got the whole system cleaned out. But it was quite the process trying to collect this material at the pump room and get it flushed around the system and separated. So later on in the program, I think Bob's got some great illustrations of equipment that's really intended for separating things like this out of the system.
And what was causing it, Jeff? Why so much on this one job? What was the catalyst for this?
Catalyst was raw city water mixed with methanol as an antifreeze in the system.
Oh.
So you had corrosion in the metal ferrous piping of the system. We can only surmise that there's something with the molecular makeup of the rubber flex hoses, or perhaps there's some oxygen permeability of those rubber flex hoses, but there's a mechanism there that had this material depositing inside the hoses.
Huh. Sounds like some of the old radiant hose that we had out there that would sludge up from some of the early tube that didn't have oxygen barriers on it. We ran them in high temperatures, and this is what we saw come out of those systems.
If you found a hard crust here, I would almost bet that these hoses, which are essentially like automotive radiator hose or something, but they're rated for about 100 psi or better,
yeah.
May be contributing to that, and it might be an oxygen barrier issue.
Yeah.
So, more room for research.
Yeah.
Hope we got some ASHRAE members out there.
Mm-hmm.
Here's one that Bob can talk about. I think you probably had some direct experience with this one, perhaps.
Yeah, and just recently, about a month ago now, it was a system I actually worked on 12 years ago. I hooked the boiler up to the system. It was a system that the homeowner had installed here in Missouri. I won't say the brand of the tubing that he used. It was a tube that he had put in himself, and he asked me to connect it, and so I put this system together. And then he called me here about a month ago and said, gosh, I got water seeping out in the basement around where the heater is for this system. He said, can you come over and take a look at it? And this is what I found. And this was, again, filled with just city water, and you can see that it's actually completely corroded the media from the air purger in there, and also pinholed the expansion tank as well as the copper pipe. Anywhere there was copper pipe that was in the system, it was turned. It had these green marks on it, and you can't see in the picture, but there's actually pinholes where those green spots are. So, again, I have to say that was an oxygen permeation issue in the type of tubing that was used in the system, running at the elevated temperatures. It was a staple-up job, so it was running pretty warm temperatures. But, I mean, that's what had happened, is that it attacked not only the least noble metals, but even the good metals in there, the copper pipe, the steel expansion tank, as well as the media. I believe that's a brass media that's coated or plated or something. I'm not sure exactly what that's made out of, but I mean, that's not something you want washing through your tubing in your system, because that's going to do exactly what the picture before it showed with the ferrous components. It's going to start plugging up your tubing and your zone valves and different components in the system. So yeah, I mean, it just keeps happening. It's something that you really need to pay attention to and check these systems and make sure that they're commissioned right in the first place. But even all those steps, if you've got a product in there that's causing, oxygen to get into the system, this is going to be an ongoing problem. Yeah,
and I say, as I look at that, I think, oh, gee, I wonder if maybe this was softened water that went into that. Do you have a recollection whether this was on city water or well water?
It's on city water. It's in the city of Springfield here in Missouri, so I know it's on city water, and there is no softener in the house, so I know it's not softened water. It's just filled right from the cold water, tap coming into the house.
So yeah, it looks like a reasonable mechanism from my experience there.
Yeah, I'm chalking this one up to the non-barrier tubing that was used in it, but. You're right. Unless you get somebody to analyze every one of these jobs, which can get expensive and time-consuming, you really don't know. You just make some assumptions based on your 30 years of doing this and seeing the same thing over and over again. At some point, you realize what the common denominators are there, and I don't know how you can deny that.
Yeah. Right. Yes. Well, this next slide appeared in the January issue of the ASHRAE Journal. And it can be referenced back to Electric Power Research Institute study. But it shows someone with some of this reddish-brown grit, which is actually ferrous pipe scale or deposited ferrous material from corrosion in metal piping. Very similar, same material as we had on the graph paper previously, just in a much smaller, finer grit. And then we also see some greenish pipe scale, obviously from copper-type tubing and rapid redeposition and such inside this brass strainer fixture, probably going into a Y strainer assembly. From a similar situation, again, these are the result of poor fluid quality in hydronic systems and causing repeat maintenance and problems with the equipment, plugging up strainers, filters, and so forth at equipment, and creating a lot of downtime in their repair. So some questions. Bob, I don't know if this slide came by way of if you brought the slide in or if John sent the slide in.
Yeah, I brought the slide in because John Siegenthaler asked the question. He said, well, what about the tubing that we're using in geosystems? It's not a barrier tube. It's just a regular PE tubing. Is that a concern? And so I just put a picture of this. Is actually a loop that you can tell there's a pond in the background. I put this in a pond loop here at my house last summer, just replaced an older system and updated it. But that was the question, and I put this in the trigger, the question that we ask you, is it a concern in the geosystems that we're not using barrier tubing, or is it the temperature that they run at, it's not so much of an issue as it is a higher temperature system?
This could be a matter of academic question. From my personal experience, I feel that corrosion by O2 permeability is more an issue at higher temperatures than it is at low temperatures because, as I said, the solubility of a metal doubles with every 10 degrees in temperature rise.
Yep.
But, and so because all of our geothermal installations are going to operate between temperatures in the mid-20s to as high as perhaps 100 degrees, we're less likely to see those issues. But with the geothermal, I really feel that the original quality of the makeup water is the determining factor in how that system's going to behave.
As well as the fluid, if it's an antifreeze fluid, being a good quality with inhibitors in it that's blended with the water, not just the pond water with some methanol in it, as you showed in the first one.
Fluid or the presence of inhibitors in the makeup fluid that are going to be the big determining factors there.
Yep.
I've seen lots of systems made up with both propylene and ethylene glycol. Not that we sanction the use of ethylene glycol, but I've seen it used. And regular tap water or city water, and those inhibitors were early depleted. And any expansion tanks used on those systems typically perforated within 5 years' time and ended up being replaced. Pump bodies rusted on the interior, oftentimes to the point where their suction intake rings became loose and started clattering around, and you realized there was a problem inside that pump. So that's where I relate back to water quality and the chemistry of that original makeup water and the presence of inhibitors and how they behave. It's interesting to open one of those old systems and start filtering it through a bag filter and find all the, shall I say, milky sediment that's captured in a bag filter just because they were inhibitors that came out of solution. And notice that the antifreeze has more of the odor of a rancid pickle juice or silage.
Yeah.
And you know that bad things have been happening inside those systems. System quality. Oftentimes with the antifreeze suppliers, they will pre-mix and bring it to the site in trucks for commercial projects. What we typically do is we keep a DI column at our offices, and a service comes around and they'll replace that every month. They'll exchange it for a new media bed. But we'll run chlorinated city water through the DI column. The water coming out of the column is the same quality as you would have with the distilled water. And a neon lamp on that column tells you whether your discharge water is of good quality or if it's containing minerals and the column is being depleted and it's time to get an exchange. It makes it very easy because we can fill a 500-gallon tank in one of our trucks and cart that to a job site and then pump that down into the systems to fill them. On commercial jobs where you may have as many as 4 of these columns all ganged up and run together and then feed them from city water to flush a commercial system. But the expense of doing this is far less than the expense of trying to maintain a system that's having problems with scaling and corrosion because you didn't take the necessary precautions.
Yeah, so you would just get a chemical regimen that's trying to correct the problem of the bad water that's in there, so you're just adding every couple of months an inhibitor chemical when in fact you should just be changing the water out and putting better quality water. I knew a contractor in Utah that did a lot of snowmelt systems, which were, high capacity fluid systems. So he kept one of these, I think you can get them from Culligan, you can rent them, these DI machines, and he would just take that right to the job with him and just buy, 100% glycol, and he would just mix it to the percentage that he wanted for the job right on the job site. It's just, easier and cheaper to buy the glycol, full strength like that, and then just blend it to whatever mix you want on the job site. And he always used one of those things, and I knock on wood, I've never seen a problem in any one of his systems, but there was, as you know, plenty of glycol pinhole problems over the years.
Very, very, very true. It's oftentimes the most economical way to do things.
Yeah.
But when you're working with a DI column, you want to use a treated chlorinated source through that. I would never consider feeding someone's well water through my DI column. You can have background bacteria and such in well water that might populate the resin in that column and then get transferred over to future fills. So you want to treat that as though it was medical equipment and make certain that it's used only with a treated, shall I say, municipal source water, preferably of very low hardness. Because the columns will last much longer, and that chlorinated water supply keeps you with a clean column, and you're not causing contamination to a glycol solution. This might be a great time to interject that the glycol manufacturers will state rather definitively that when you start working with glycol concentrations less than 25%, you dramatically increase the possibility of bacterial contamination. So you can get slime growing and so forth in your glycols when you're working with concentrations less than 25%. We ran our tests at 20% solutions because we were mixing with clean water for the most part. But if there's any situation where a makeup water might come from the city's supply, heaven forbid that it would, but if it did come from an outside supply, it's best to keep that glycol concentration at 25% or just a little bit higher to try and forego any possibility of a bacterial growth within that glycol solution. Bob, this is one that you brought into the program, and this is probably a hot water scaling situation, I would suspect.
Yeah, it was
from a domestic distribution.
Yeah, one of the Bradford White reps had this at a seminar I was at recently. He was doing water quality and for water heaters and tanks and vessels and stuff like that, and he had this little sample that he cut away of, they're getting a reduced water flow to this apartment or whatever this hotel building was, and that's a 4-inch copper main with, I believe, a 2-inch branch out the side, and that's what hot water, again, the hot water is making that precipitate out, I believe, Jeff, is that's the case.
Absolutely.
No. On that. And just trying to cut that out of the system, as you can imagine, it was like cutting through rocks with the Sawzall blades to get it out of there. That's when they knew just wrapping on it with your knuckles and then trying to cut it out, realized that that's what was happening is the hard water was just precipitating out in the hot water mains and coating the inside of it.
Those are just amazing to be able to show those. And did the Bradford White fellow have a solution for this problem?
Well, I'm assuming it was going to be some type of softening equipment in there because, the water supply is what the water supply is. So you either you treat it or you deal with problems like this. But I think the other thing that he had indicated was running at a pretty high temperature, on this system. And from what I understand, the hotter you run the water, the more minerals precipitate out of it. So if the tank's running at 140, 150 degrees, you're going to get more of this precipitating out. But I never did hear what the final fix was. But gosh, if the whole building looked like that, it was probably a repipe to begin with, and then correcting the water issues before you build this up again.
Well, I suspect that this is a water supply that had perhaps a well as its source, and had relatively high carbon dioxide content to it before it got to the water heater. And that carbon dioxide keeps the calcium in solution, calcium and magnesium. And that after that carbon dioxide was released by heating it, the only option available there was for that calcium and magnesium to start crystallizing out. And this is what we get tree rings inside our plumbing.
Yeah, that was incredible. And as you can imagine, it weighed like 15 pounds.
Oh, yes. It's like the coffee pot that never gets cleaned.
Right.
Yeah.
So, actually, I think from here on out it's probably what I've got going on. We've got about 10 or 15 minutes here. But now what I will say is I want to show you some of the Caleffi product that we have that can address some of these conditions. Now, we can't, with a brass device or composite device, we can't fix bad water quality. I'm not going to, and I think you realize that that's not the intent of the products that we're going to show you here, but I mean, it happens on products with domestic water. Here's one of our quick setters that was used on a domestic water system, and it and the same thing, it started plugging up, the flow was being reduced going through it, and we got it back to the factory and looked through it, and you could barely see through the end of that because it had closed up with the hard water deposits on that domestic hot water line that it was being used on. Now, again, a strainer isn't going to fix that, a separator isn't going to fix that. You really have to address, the fluid that's going through that device. But
hey, Bob, a question came in, and this slide's probably good to address it. This is Mark. Jeff, you mentioned that water will, basic minerals will precipitate out as a function of temperature. So the higher the temperature, the more problems you have with hard water. Is there any function as it relates to calcification of pipes regarding the velocity of the fluid traveling through it? I mean, does fast fluid, is it more forgiving?
Yes, faster is more forgiving because a higher velocity in the pipes helps to, shall we say, erode or abrade or keep that scale from forming. So speed helps reduce the amount of scale formation inside the lines. And
so if an engineer was simply on a hot water recirc, just trying to overcome the temperature loss in the pipes going up to the fixtures alone, that calculation might result in a fluid velocity a little bit less than optimal as it relates to scaling.
Well, let me think here for a second. Higher fluid velocity is going to wear the pipe away faster. You'll have more pipe corrosion if it's an aggressive water, but you'll help limit the scaling if it's a scale-forming water.
Yeah, that's like a catch-22 question. Like I say, if you could open at 4 per second velocity, you might keep your pipe scoured, but then you could, pinhole from corrosion, erosion from the fluid going around elbows and stuff too fast.
Yes, you'd find those turbulence places and erosion, right.
Yeah, so you're trading off one problem for another. Huh.
Okay, I thought it was a good spot for that question.
Yeah, thanks.
Mm-hmm. Oh, that's another one of yours.
Yeah, and this is, again, sent to us. It's one of the small diameter tube ModCom boilers. I don't know if you can see in the picture, but that's actually water spraying up through a pinhole in there. Now, this, as I believe, I don't have the complete story on this, kept taking on makeup water, so it was, you can see the little cutaway of the tube there. It was getting deposits on the inside of it, and so now when the flame came on inside this heat exchanger, it wasn't getting the heat to the water. It was actually becoming an insulator on that tube, and then you can see by the color of the tubes there where the burner was going in that it was overheating it, and it finally fatigued the metal to the point where it developed a pinhole. So two things to be said on this. Obviously, this was a closed-loop hydronic system. Now, we're not looking at a potable water system, and it was a case of, taking on water constantly. It had a leak in the system somewhere, as I recall, and it was taking on water, plugging up the heat exchanger, or at least coating the heat exchanger so that you didn't get the heat transfer to the water and then stressing the metal. So, number one, check, make sure you don't have leaks in the system. Put a gauge on it, monitor it for a while. But, yeah, you can't keep putting fresh water into a closed-loop system, especially water that has, hard mineral deposits in it, or this is
it's a problem. Yeah, you don't get your heat transfer and things get too hot.
Yeah, just don't assume because it's a closed-loop system and you filled it up on the first day that's good and there forever. And I think this is one that you sent, Jeff, with a similar type of boiler.
Yes, this is a situation where the boiler, the body was not level within the frame, and it was causing condensate to pool towards the front side of the boiler. That condensate becomes very acidic and not flushing itself completely through the condensate drain at the back of the boiler was likely the explanation for perforations at the weld seam around the front side of the boiler.
It's even eating away the concrete block below it there.
Yeah, it's eating away the concrete block underneath. That's right. And there's about a quarter-inch divot in that concrete block where the condensate was dripping out onto the block.
So real low pH in that condensate water.
Oh, yes, yes. And here's one that you provided.
Yeah, and I mean, one of the selling features of this type of boiler was it had a self-cleaning heat exchanger. That it was a tube type of boiler instead of that little serpentine coil, and they say, oh, yeah, they're self-clean, they won't plug up. But again, you know, garbage in, garbage out. It's like the early days of computers. Whatever you put into them is what they spit back out. If you put bad water quality, you keep adding fresh water or hard water or rusty water, something like that, into a heat exchanger, it doesn't matter that it's a self-cleaning design. It still has the potential to plug up, and of course this is going to overheat and fatigue the metal, just like the other type of heat exchanger on the different style boiler.
Yeah, I looked at this one and I said, my goodness, whatever they were circulating in this radiation system must have been nasty, nasty, dirty water, or it had a leak somewhere in the system and was being made up by water on a continuous basis, because
exactly
this is time accumulated rusty mineral scale telling me that there's other ferrous metals in the system
that are going bad,
along with hard water that it's not getting flushed out and cleaned out.
Yeah. Now that is something that, you know, we had to have some products from Caleffi that can certainly minimize this, but I mean, if you got to find the cause of the problem. I mean, you can't just put a Band-Aid on it if this is going to keep going on. We have separators that can deal with that. As long as that can get flushed through the piping, if the pump can move that through the system, you know, the various separators we have will remove that type of particle, as well as that magnetic stuff that we showed you earlier, and we'll show you a couple of products. But again, we don't want to sell you a product to treat a symptom. You got to find the cause of it and keep this stuff out. But we certainly have products that are designed to handle this type of residue.
Right, but this is a low velocity, very low pressure drop on the water side up here, so there really isn't a lot of force to try and flush this stuff through this type of a boiler. It's nice because you can do total circulation through them, but it means having a clean system to do that.
Yeah, and that's the trade-off. I mean, we don't have the velocity that we did in that serpentine coil before it, but this is the other side. You won't, you know, like you say, scour these tubes because of the low pressure zone type of deal.
Right.
All right, yeah, we're going to run
Oh, you can talk on this one. I'm excited about these.
Yeah, this is going to handle a lot of problems. This is a product that we've introduced, and a couple things that's unique about this. It's a composite body, so we're not going to have any issues with dezincification if the water becomes aggressive. But what this device does, it's a separator, a dirt separator, but it's also got a magnetic band. So some of those slides that Jeff showed a little bit earlier, where you had those ferrous particles that had just kind of adhered together and you know, stuck to the inside of that rubber hose on those Geo systems. As long as that is moving around through the system, we can catch it with this type of device, because in addition to having a median here that's going to catch the big particles and scrub them out and cause them to fall to the bottom of the cup here where that valve can flush them out, it's got a magnetic band that's going to get those tiny little, almost like shaving lead off your pencil with your pocket knife, that type of debris that over years is going to build up, and finally it can plug up the tubes or the pumps or the zone valves. This device here is going to get that. Now, obviously, you're going to have to do, this is one actually on my shop. I've got it on a big solar steel tank that I have. It was an old LP tank that I turned into a solar storage tank, and every couple months I go out there and put a cup, and I'm not adding any new water to it. It's just the debris that was in that tank when I converted to use. But I put that clear plastic cup under it, and you can see with the little pocket magnet there on the left-hand picture that is ferrous components that's washing out of that tank. And that magnetic band on the bottom of that captures that. I take the band off, open the valve on the bottom, put a cup under it, and I can flush it out and see what comes out of it. So I think it's going to be a really popular component for us. It's going to be, you can see the brass ring. You can turn it horizontally or vertically, applications for that. So that's what we call dirt mag, so it does dirt and magnetic particle removal.
And I'd say as we start to work with variable speed circulating pumps that have permanent magnets in them, devices like this are going to become more essential.
Yeah,
So
yeah, I think it should be.
This is not something we want floating around with a wet rotor pump.
No, we don't want it in the
magnets in it.
Right, exactly. An ECM pump that has a strong permanent magnet type of motor. You can see this is just a powder. If you were to pour that out, it almost looks like, I say, like you took your pocket knife to your lead on your pencil and shaved it. It's a really fine powder, and it's going to go and it's going to get into those pumps. So you can see with the magnet that comes off of our dirt cal there, stuck to the outside of a clear plastic cup here, and you can see how it attracts those particles. So yeah, this is going to be a key component with the new types of pumps on the market. And then, of course, we've got some bigger products that are available. These are dirt separators. You can see on the right there on some of our brass, different versions of our dirt cals, we are adding the magnetic bands to those also. So if you need larger sizes, that magnetic band is available for you can see we've got some verticals there as well as some horizontal dirt mags that'll get the big particles, and of course, in the larger flange steel versions there on the left. What else do we have? A new product that we're going to introduce, that we did introduce, I should say. This is a 4-in-1 product that we're excited about, and this is going to do hydraulic separation as well as good dirt and air removal, because we put a full-length media in there from the top to the bottom. So it's a true 3-in-1 device that we can do hydraulic separation, good air removal with a high-capacity air vent on the top, and then again, real good dirt removal with the full-length media. And what else did we have? This one probably rotates in if you click it again. This is a new product, the SEP4, and this is a true 4-in-1 device. Now look what we did here is we put the top of our regular air separators on that, so that's a serviceable top. I don't know, you can get to the float and get to the stem on the top of that, and we put the magnetic band on the bottom of it, so now you've got hydraulic separation. As you can see, it's a 4-port hydro separator. We've got the full-length media in there to do a good job of air removal at the top, dirt removal at the bottom. We've got a convenience port for a sensor well or a temperature gauge up near the top, and then we've added the magnetic band to the bottom of it. So this is probably going to be a great application for just about any job, whether it's a new installation or a retrofit on one of those systems that Jeff showed where they've had some problems with corrosion in there. This would be a device that can grab any of those. And again, you can flush it out.
Like a universal for a lot of things.
Yeah.
And I like the insulation jacket that I see that goes around behind things, so that it can serve in geothermal, it could serve in solar, it could serve in a chilled water system.
Yeah,
too.
Thanks for noticing that. It does come with a 3-piece, actually a 4-piece, the 2 front and back halves and the top and bottom, so that if it is used in a chilled water application, which it certainly should or could be, it'll keep that from sweating and dripping. And looks nice too. There's a little better picture of what goes on inside of it, and the insulation detail on there with the media top and bottom and the good air vent on the top. All right. Oh, there you go.
We're almost done.
Yeah, we got a couple more slides. Thanks for hanging in, everybody. I can see people are sticking on there. This is tell us about it. This is your book just out, or when did you?
Yeah, this is just out. We worked on this for 2 years. I spent this past year circulating through committees with refrigeration service engineers to get the comments of various committee people. And just here before year-end 2012, it went to print, and it's now available in the RSES bookstore. It's a 200-plus page manual written as a primer for geothermal systems for those people who are involved with specifying, for installing, sales of geothermal. We talk about just a multitude of installation situations and how to overcome problems, examples, and corrections. So that's why I say it's one of those texts to help supplement people who have had IGSPA training to design ground loops and so forth, and it takes us another quantum leap beyond just training to do the in-the-ground part of geothermal, but looking more at the equipment installation, water quality issues when you're working with open loop systems and well waters and so forth, as well as closed loop systems and solution water quality, antifreeze quality, so forth. And a lot of the, shall we say, I don't want to step on too many toes, but installers sometimes have a few X chromosomes and don't read the manuals or don't read the books. And so it's about reading the fine print on the electrical diagrams and how to set up the control boards and such, and make sure that these machines are going to operate the way they're intended to operate.
Well, good for you, and I hope that you sell 1 million of them. That's a good resource to have. And if people want this, obviously we'll make these slides available. Or you can do a screen grab right now, and you can capture that, email address if you want. So.
But so it's a good read, and has lots of real life stories in there and experiences, and we cover the three major manufacturers on equipment, just a multitude of equipment varieties, methods of installation, and so forth.
Great. Well, I'm going to get a copy.
So pass on to the next slide.
Yeah, I think we're about to just some housekeeping details here. I think that's our hydronics layout. Number 12 just came out here this January at the ASHRAE show. We kind of unveiled that. That's on hydronic fundamentals again. It just kind of takes you through the basic steps of designing the system, and it references some of the other ones, so we didn't get too thick on that. So if you're not on our list, make sure you go to the website, caleffi.us, and sign up, and we'll get you on the mailing list and mail those out. So that's that. Next, please.
I might add that hydronic fundamentals should be in everybody's bookshelf.
I think
really.
that's going to be our crowd pleaser bestseller. Our Geo and our solar ones have been our biggest, most popular. But I think that one's going to overtake them all because it is so well written, and it just really reminds you of all the basic things that sometimes you just need to read that again and remember that. And it's of course updated for the modern day components and stuff too. So. And
all of these manuals are extremely well illustrated, and it's not just an illustration, but it's an illustration with descriptions as to what's there and what they do and what their purpose is and so forth. So,
yeah, thanks.
I've been collecting these for a long, long time.
Well, thanks for that plug.
And that's why I was so excited when you offered the opportunity to participate in the webinar.
Well, and thank you for your years of experience. I know it's hard to jam all that into an hour's worth of time, and I know we're running over here a little bit, but if you get to see Jeff at some of the different associations and stuff where they have meetings and get together, definitely sit in on the seminars because you'll learn a lifetime's worth of information there. What do we got left? I think that's about it. A couple things, just upcoming stuff. The next couple hydronics coming out, we'll do one on cooling systems. That'll be nice, radiant cooling, different hydronic cooling systems. Will be out sometime in July. And then next year, we want to get into more on wiring schematics and stuff. That's one of the questions we always get. So that'll be an excellent one on how to wire different hydronic and probably some solar controls in there. What else? Diplomas on the next slide. I think if anybody wants one of these for any of their continuing ed creds or something, they'll be available to people. Mary will send these out, so it takes a couple days to a week before you'll see it, but we'll email them directly to you, so you'll have a record that you attended today. What else? Coming up on the next slide. That's what we've got coming up for the next couple months. Solar thermal on the next one. Some engineering innovation, and then cooling down. John Siegenthaler is going to sit down in this one. He's going to do some hydronic cooling session for us. That should be really good. And then Mark